Okay, this is just a general methodology for solving one-dimensional problems in momentum. So solving 1D momentum problems. Just sort of a general set of rules of things you should be looking for as you're looking at a problem to try and decide, is it momentum, is it one-dimensional? Because there are two-dimensional problems too, and one of the most common mistakes on the second exam is actually doing a two-dimensional problem as a one-dimensional one. So I do want to mention the difference here and again in the two-dimensional problem section. And then how do you go about solving a problem once you've identified it? So first, momentum problems tend to offer a lot of information relating to initial and final velocities. Now, that doesn't necessarily mean it's a momentum problem. There's a chance that it's an energy problem, and you can do it with kinetic energy. The thing that will split the difference on this is there will be some kind of interaction. Collision, explosion, something like that. The reason why that's significant is energy problems don't deal well with actual collisions between two objects. They really don't handle that well at all. If it's inelastic, you can forget it. Energy methods will be a disaster. So if you meet those two conditions, you should be starting to look in the direction of a momentum problem. Indicating one dimension, you will not see any mention of angles. If there's mentions of angles, that inevitably is pointing you at some kind of 2D problem. And you should leave behind one-dimensional techniques at that point. Let's see, is there anything else that can give you a hint? Can't think of anything offhand. Generally, if there's any kind of mention of angles or components, like x and y components, you're pretty much looking at a two-dimensional problem. All right, once you've identified that's what's going on, what do you do? Well, first thing, determine the type. Is it elastic? Is it just plain old inelastic? Most of them will be, or a lot of them will be. Is it a special case? In other words, is it an explosion type? One object splitting apart to many, or is it perfectly inelastic? Oops. If it's either of those, you get some special rules, and that makes it easier to solve. Second thing, draw your initial and final states. Identify everything you know about those states. Then finally, write your momentum conservation statement. And, if elastic, your kinetic energy conservation statement. What will those look like? Well, it varies depending on if it's a special case or not. But generally speaking, it'll be something like M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. That equation will always appear in a momentum problem. You may get lucky and your V1 final and V2 final may be the same thing. If it's perfectly inelastic, or if it's an explosion, your V1 initial, V2 initial may turn out to be the same thing. And it simplifies the problem a little bit. It's like getting free information. It's very nice. If you get the kinetic energy conservation, if elastic only, then you also get 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared equals 1/2 m1 v1 final squared plus 1/2 mass 2 v2 final squared. Okay. One-dimensional tends to be relatively straightforward. Most of the time you're being asked to find one of the speeds or one of the velocities. Only in extraordinarily rare occasions are you asked to find one of the masses that results in something, but there is a chance it can show up. So keep an eye out. Any of the parameters here could show up in yours as your solution. So there are a total of 6 parameters. If you have 2 equations, you can handle not knowing 2 of them. If you have perfectly inelastic or explosion, that actually eliminates one of them for you, which makes it a little easier. So there are only 5 parameters if it's a perfectly inelastic or an explosion type. I think that's going to be it for this video on one-dimensional problem solving. Eventually we will have some example problems, so make sure you keep an eye out for those. We'll stop it right here.